Good morning, everyone. I am Lahal Chahine. I am a third-year PhD student at Tyram. I work within the Horizon 2020 ITN Astrochemical Origins, ACO. So today I will present you the work we have done on OMC2 FIR4, in which we have observed shocks and filaments at 100 AU scale. So to find OMC2 FIR4, we have to go to the Orion Nebula, particularly the Orion A cloud that I show in here. And you can see that there is this filament that looks very dark in infrared. It's called the integral shape filament. And this filament, when you observe it in millimetric, we can observe that actually it harbors several forming cores, star forming cores. And there is this region in here, which is far infrared 4. If we go and observe it at high resolution, around 100 AU, you can see that it's actually a protocluster that harbors several protostars within it. So in addition to being a protostellar cluster, OMC2 FIR4 actually has a very particular environment. So as I said before, we have this integral shaped filament that it was observed with N2H+ by Hakar et al. In 2018. They have observed it with almost 1/6 scale, at 1/6 scale with 2000 AU resolution. And they have revealed that actually the ISF is a collection of fibers and what is called hub associations that you can see in here. And OMC2 FIR4 actually is one of the hub associations. Within this hub, we think that we should have filaments, or what we call intra-hub filaments. But with the algorithm that Hakar et al. Have used, they could identify one filament, one fiber within OMC2 FIR4, which is this one in here. However, the other filaments within the cluster were not resolved. So here I show you the N2H+ emission by Hakar et al. At 0.1/6 scale. And you can see that there is this fiber in here, but the main region in OMC2 FIR4, in this main region, we couldn't observe any intra-hub filaments. So one of the main questions is, are there any filament within OMC2 FIR4? And what could we find if we observe this region instead of observing with N2H+, if we observe it with methanol, CS, or SiO? SiO is a shock tracer, and CS and methanol probe the dense gas, and they could also give us a vision on the dynamics of the protostar cluster. So to answer this question, actually, we need a resolution which is better than 600 AU. Another particularity of the environment of FIR4 is the presence of jets and outflow. So it's known that there is outflow from the source HOPS 370 in FIR3. It's located to the north of FIR4, and it's known that it has an outflow that overlaps with FIR4, at least in projection. The outflow was observed with several molecular tracers like Sio, but it was also observed in O1 emission by González Garcia et al. Another characteristic is also the presence of a jet that was recently observed by Ratanzi et al. This jet is driven by the hot Corino HOPS 100Na, and it's shown in here. So one of the other questions about this protocluster is if the outflow coming from the north, so from HOPS 370, is really impacting and triggering the star formation within OMC2 FIR4. And for this, we have still a debate. Some researchers say that there is no impact. Actually, what we see is only a projection effect, while others say that there is an impact. So to summarize, OMC2 FIR4 coincides with fibers hub association, where we think that we should observe intra-hub filaments. It's a protocluster in which star formation is going on, and there is an outflow or a jet from its north that could be or not impacting it. And it's also located near high mass stars that have H2 regions and shells. So what's really going on in this protocluster? To answer this question, we had to observe OMC2 FIR4 at an unprecedented angular resolution. And we have observed with several tracers, SIO, that, as I said, traces shock, methanol, CS, and other tracers that trace dense gas, and that could give us a view on its dynamics. So here I show the emission of CS. In this figure in here, I have the CS emission in yellow at 3. The emission starts from colors, start from 3 sigma. And I have here in cyan the contours of methanol emission at 10 sigma. We have labeled the protostars with with star symbol, and we have this triangle symbol that stands up for the SIO peaks that we see from our work. We have also, to represent the direction of the outflow from HOPS 370, we have drew these 2 arrows. This one goes in the direction of the R1 jet observed by Gonzalez Garcia et al. This arrow is perpendicular to the disk of HOPS 370. And these 2 arrows have goes in the direction of the SIO peaks that we have observed in our work. So to describe the CS emission, first, CS is a typical high density gas tracer, and CS shows the brightest and most extended emission in our maps. So it probes the overall structure of the gas. You can see that we have this main filament in here that goes from the northeast to the southwest, and that we have called the eastern ridge. We have also, with CS, we could see also several filaments and cavities that goes from the north to the south. Here I show the methanol emission. We have mapped 2 different transitions. And you can see that we have a similar morphology with respect to what was observed in CS. We see these interwoven filaments in here. And we can also see cavities. And with this methanol transition at 218 gigahertz, we could also observe 3 class 1 type methanol masers along the eastern ridge. With the other molecules, we see also a reasonable agreement. And we can see that this eastern ridge is traced by all the molecules. And there is the central collimated filament that's very well traced by CS and H13CN that are the tracers with the highest critical density among all the tracers that we have. So they are tracing the very dense gas. So we see an agreement between the tracers, except for SIO. But before showing you the SIO emission, I would like to compare what we have in here with respect to what was observed at larger scales. So here we show the N2H plus emission from Hakar et al. And if we zoom a little bit, you can see I show it here in green. The N2H plus emission is shown in green. And we have overlapped the CS contours from our maps. So we have different angular resolutions. So the one by Hakar et al. is 2000 AU, our resolution is 100 AU, and also the tracers are different. But the studies might be complementary. Actually, if you can see here, the fiber 43 that was identified by Hakar et al. Especially coincides with our eastern ridge. And we could see these filaments in this region, and where this region that was not resolved with N2H plus. So actually, with our study, we suggest that we could reveal the intra-hub filaments within OMC2 FIR4. Here I show the same map, but with methanol emission, with methanol contours from our study, and it's also seen that we could reveal the intra-hub filaments. So it's like the N2H plus is tracing the skin, while methanol and CS are tracing the bones. So concerning the dynamics of the filaments, we have here I show the moment one or velocity maps of methanol. So we could see that we have each filament is characterized by a different velocity, where we see that the higher blue shifted and red shifted velocities are located at the filaments are located at the center of the protocluster. And we could also observe the east-west velocity gradient of almost 4 kilometers per second. Here I show the velocity dispersion maps of methanol, and we can see that we have the external filament have a low velocity dispersion of less than 2 kilometers per second. The filaments here, what we have called intermediate filaments, they have a velocity dispersion between 2 and 4. While the highest velocity dispersion actually is observed at the center of the protocluster, and we see a dispersion between 4 and 7 kilometers per second. On the other hand, with N2H+, the velocity dispersion was between 0.2 and 2.2 kilometers per second, which is much less compared to what we see. But this is expected because the tracers are different, and actually methanol has allowed us to have a deeper view on the dynamics within the cluster. So having this higher turbulence at the center, higher dispersion suggests that we have higher turbulence toward the center of the protocluster, and this could be due to the presence of the protostars along the filaments, or also could be due to the presence of outflows from the forming stars. So we needed more action, so we went to observe SIO. And here I show the SIO emission in yellow, and we have the methanol contours in cyan. And you can see that we have a dichotomy between SIO and methanol. So the SIO emission is mainly located at the west of the cluster. And with SIO, we could observe multiple bow shocks. So you can see here what we have called the ARC1, which is an extended bow shock. And we have also here the ARC2. And we have, or we could also reveal a collimated jet from the protostar VLA15 that goes in the north-south direction. So this jet is revealed for the first time. And VLA15 actually is an embedded star that appears to have a net-joint horizontal disk. So the geometry of the bow shock in our map suggests that they might be created by a precessing jet from the source of 370 that goes along the cloud or the filamentary structure, and it's precessed from east to west, creating these bow shocks that you can see in here. So we have also seen the SIO dynamics. So here I show the velocity map of SIO, and we could see that it extends at much higher blue shifted and red shifted velocity. Actually, we could observe 3 different velocity regimes. We have the blue shifted high velocity regime that it goes between -17.6 kilometers per second and -8.1 kilometers per second with respect to systemic velocity. And it traces this part in here, which is the ridge and the jet, and this bow shock that you can see in here, the ARC2. We have a blue shifted low velocity regime that probes the bow shock in here, and we have a red shifted low velocity regime that probes this filament in here, and another bow shock here. With the velocity dispersion map, we can see that the dispersion goes between less than 1 kilometer per second and more than 10 kilometers per second. We have a very low dispersion at this ridge in here, while the dispersion becomes higher along the bow shocks. So what we have done is to overlap the integrated contours of the different velocity regimes in SIO. We overlapped them on the methanol, CS, and H13CN emission. And what we could see actually is SIO is tracing filaments. So the high velocity blue shifted component is tracing this eastern region here and another filament in here, while at red shifted low velocity, we can see that SIO is actually even tracing this filament in here. So despite being a little bit, the SIO emission is more located toward the west, but we could also observe this SIO signature on the filament. And this suggests that the gas is being compressed and warmed up. So there is a mechanism that goes in this compression of the cloud and creating SIO shocks. What could be this mechanism? Well, we have two hypotheses. It's the first one are the expanding shells. The second one is the outflow. So as I said before, OMC2 FIR4, which is here, is located nearby high mass stars that create H2 regions and also expanding shells. So several expanding shells were observed in CO around FIR4. We can see at least 3 here that were observed by Federson et al. And we think that one hypothesis about seeing this SIO along filament could be due to the collision between these expanding shells and the OMC2 FIR4. The other hypothesis would be is the outflow. So we think that the SIO signature on the filament could be due to could be a fossil imprint left by the precessing jet from HOPS 370. So the jet that precessed from east to west have created these shocks, and we see this fossil imprint in here. So now I go to the conclusions. We could see the intra-hub filaments in OMC2 FIR4 for this first time using different molecular tracers like methanol and CF. We have seen that the filaments have different velocities and that we have higher turbulence at the center of the protocluster. We have seen several bow shock features in SIO due to the jet driven by HOPS 370 that precessed from east to west. We could observe for the first time an SIO jet driven by BLA15. And we have SIO signature along the filaments that could either be due to expanding shells or to outflows. And in order to assess better this result, we need the hypothesis, we need to have more molecular line observations. Thank you for your attention.